Hi, my name is Amore Trio. I'm a professor in the School of Physics and Astronomy at the University of Birmingham. My research is on exoplanets. Exoplanets are planets that orbit other stars than the Sun. Imagine something similar to the solar system, except that at the center there is a star that is not the Sun, or more than one star. Sometimes those stars are similar to the Sun, and sometimes they're very different. Exoplanets are interesting because they help us place our solar system in context. They also allow us to search for evidence of extraterrestrial biology in the cosmos. The topic is an important topic of modern astrophysics, and indeed it was recompensated by the Nobel Prize in Physics in 2019, which Michel Mayor and Didier Queloz obtained thanks to the discovery of the first exoplanet, which they made in 1995. And in 25 years of exoplanetary detections, the most important and interesting thing we've learned is how diverse exoplanets are. Planets are diverse from one another, they're diverse from the solar system, but also their systems, like the type of stars at the center, are quite different from what we're used to. And that's what we will look at in this presentation today. We will talk about Tatooines, planets with two suns, hot Jupiters, gas giants that are hurling close to their stars, and super-Earth, planets bigger than the Earth but closer than Mercury is from the Sun. This, I hope, will take you on a journey of discovery of exoplanets and pick up your curiosity into what is, I think, one of the most interesting topic of active research nowadays. So first, let's have a look at the image that we have in the background just there. This is an artist rendition, and a lot of the pictures that we show are artist renditions today. We actually do not see exoplanets. We, most of the time, only deduce their presence by the effect they have on the star, notably as the star can wobble back and forth. As the planet orbits it, it moves the star ever so slightly, and that we can measure. This rendition, though, that you see on your screen is interesting because it places us immediately in a different context. We see a crescent of a planet. It has a nearby bright star. And we see on the bottom left corner that there is another star in the system. This is a planet in a binary system. Unlike a Tatooine planet, the planet orbits only one star. Tatooine orbits both stars in the Star Wars universe, and we'll look at an example of that later on. But right away, this tells us by this very image that we're not in a solar system. However, the solar system is visible here. And we can see it on the top right corner, where the sun is just there. What we see here was a rendition made after a discovery of a planet around Alpha Centauri b, the fainter of the two stars composing the Alpha Centauri AB system. This is the closest star system to the Sun, so the Sun is actually appears as a bright star in the sky. By showing the Sun in that way, it gives immediately that sort of foreignness and also that reflection about what is the solar system and how does it compared to the many outcomes of nature. What is the context of the formation of the Earth? What is the context of biological life on Earth? And that is really what exoplanets offer us, and why I think I'm interested in discovering more and learning more about them. So now I will go through a series of sort of rare and exotic planets, or the archetypical class of planets I will go through, and then I will show a few graphs that explain, with the population of planets that we've discovered, how different and how similar exoplanets are to the solar system. So the first planet we'll look at is WASP-17b, and we look at this one for two reasons. The first one is because this is the biggest planet that we know so far. It's twice the size of Jupiter, you see it on the bottom right, or Jup, the radius of Jupiter, and half the mass of Jupiter, meaning that its density is less than that of Jupiter, quite a lot less, and less, in fact, than the density of water. The other reason why WASP-17 is interesting is because as a hot Jupiter, you see it's pretty hot at 1750 Kelvin, it orbits only in a few days around its star, is because of its orbit. In a solar system, most planets are within the same plane. We call this the ecliptic. This is also why the planets line up along the zodiac in the sky. And the ecliptic is almost coincident with the equator of the Sun, which led to Laplace and Kant to think that planet formation happened in a disk around the star, because it was all going in the same direction, pretty much. In the case of WESP 17b, this is not the case. The planet, as you can see now, orbits on an inclined, actually retrograde orbit. The star goes from left to right on the screen, whereas the planet goes the opposite way, but in an inclined manner. And the reason why this is a bit unknown. 30% of the planets in this class, the hot Jupiters, are inclined or misaligned compared to their star. And we are trying to find out why. It could be that there was another planet in the system, which led to some gravitational interaction, and the inner planet being promoted in inclination. Or it could be that the star itself moved, and we're trying to investigate reasons for both of these phenomena. The next planet we'll look at is Celt 9b. It's also a hot Jupiter. It's also ever so slightly smaller than WESP 17b, but what's interesting is how hot it is. Its surface or equilibrium temperature is about 4050 Kelvin. This is extremely hot. This is hotter than a lot of stars, and because of its size, which is also bigger than many stars, this object is in fact hotter than most of the stars around us. This is rather surprising. The reason it's so hot is because it orbits very close to a very hot star that you see here, again as an artist rendition on the right-hand side. So on its own, the planet cannot emit light. However, when it's close by, it receives irradiation and then it glows, just like a red-hot iron would in a way. Except that this one just happens to re-emit or re-irradiate more than a star would, which gives an idea of the kind of diversity of exoplanets that we have. And this one too is also on an inclined orbit around its star. Now what's interesting is to compare planets to stars now. It gives a good segue, and you see here the smallest star that we know so far, which is called EBLM J0555-57. This star is ever so slightly bigger than Saturn, and you can see Jupiter on the left-hand side, and TRAPPIST-1, another very important star, which is ever so slightly bigger than Jupiter. So although these two stars on the right-hand side of your screen are about as big as planets, their mass are much larger than planets, and you see below the screen the numbers. They are about 85 times more massive than Jupiter is. So what's up with TRAPPIST-1? Well, TRAPPIST-1 is fairly close, only 12 parsecs, about 40 light years away from the solar system. It's among the closer systems to the Earth. It is located just above the ecliptic, but south of the celestial equator. And around it, we've discovered 7 planets, 7 Earth-like planets. We know they're lightly rocky. They have masses and radii very similar to the Earth. And all 7 are considered temperate. And by temperate, what we mean is that in principle, water could remain on at least one part of the surface for billions of years if the atmospheric and geologic conditions are right. And we do not know yet whether those are adequate at the moment in the TRAPPIST-1 system. But it has become sort of promise for investigators like myself to search and find out whether these planets have atmospheres, and then find out whether the atmospheric composition of the system allows for the presence of liquid water on the surface, and whether it contains evidence of an active biology. So TRAPPIST-1 is extremely important, and we're trying now very hard to find other systems like TRAPPIST-1, and for this we're using a series of telescopes in Chile. You see here the Speculoos telescope. Birmingham owns this one here, the Ganymede telescope, which we use to monitor stars like TRAPPIST-1, seeking planets around these smallest of stars. And we'll see later, these smallest of stars are actually the most numerous. In terms of multiplanetary system and looking at planet diversity, look at this. This is the orrery that we could build after the Kepler mission. The Kepler mission was launched by NASA in order to find planets analogous to the Earth around stars similar to the Sun. It hasn't found one, but instead it found thousands of other planets, and hundreds of those in systems. And you can see the solar system. Here are the 4 innermost planets of the solar system, with Mars being the outer one. And the size of the dots here is respected between each of the planets. Of course, the sizes and the distances are not respected, otherwise you wouldn't see the planets. But you can see how different many of these systems are. Many have planets bigger than any of the planets within the inner solar system, but also much closer to their star. And that's, I think, a good example of exoplanet diversity as well. So what do we know about this multiplanetary system? What kind of multiplanetary systems do we have? Well, the most emblematic probably is the 55 Cancri system. This one is really odd in many ways. It has 4 gas giants, as you can see, which is already all closer than Jupiter is from the Sun, so that's quite unusual. The innermost gas giant, 55 Cancri b, is only on an orbit of a few tens of days around its star. But what's interesting is also the innermost planet, which is 55 Cancri e, which is and has become the archetypical example of a super-Earth, about twice the size of the Earth, 8 times the mass of the Earth. It's likely rocky, and we now are wondering whether we are not seeing example of volcanism. It looks like the size of the planet is changing ever so slightly, which might mean that the planet is enshrouded in a sort of big volcanic cloud, and this cloud is moving up and down depending on eruptions at the surface. Something we obviously not entirely certain about, but that is fairly exciting, so a lot of attention is being brought on that system. And 55 Cancri e is a very good example of a super-Earth. We will look at other examples later on how interesting these sort of weird planets are. Finally, we're reaching the Tatooines, the second binary planets. Second binary meaning that the planet orbits both stars of the binary. And this is the first example here. We have Kepler-16a b. Kepler-16a is the brighter of the 2 stars. Kepler-16 big B is the fainter of the 2 stars, and little b is for the planet, which orbits both of them. And it's about the mass of Saturn orbiting both of them. It's a planet that we are following at the moment to confirm its mass and other things in the system, in a project that is very exciting going on at Birmingham. Maybe an even more exciting system is Kepler-47 AB, B, C, and D, which has 3 planets. One of them is a super-Earth, and the other look like smaller versions of Neptune. And you can see all these 3 planets orbit very well on stable orbits about both stars. So second binary means both stars are orbiting one another, and the planets orbit exactly both of them in a near circular. It can be a bit eccentric. Second binary planets are odd because they cannot exist too close to the binary, otherwise they would be unstable. But they're very interesting because this unique configuration of a binary star and planets around it allows us to study planet formation and the outcome, how planet agglomerate into, our dust agglomerates into a planet. So now let's look at a little bit at a few graphs. What we have here is mass on the vertical axis here in units of Jupiter and orbital periods in years. And Jupiter is there at 1 Jupiter mass and about 12-year orbital period. You have Saturn, Uranus, and Neptune here, Earth and Venus. Mars and Mercury are below the diagram here. And look at 25 years of mass measurements. This is incredible. We have so many planets, but none really look like the solar system. And why? Well, why? The first thing is that it takes a long time to find planets. So for instance, a planet like this here is about 25-year period, or would take about 25 years to find. And so we've been discovering planets for 25 years, so it's extremely hard to find those. And the first generation instruments were not so precise. So the precision of our instruments more or less slopes around here. The easiest to find are these, which are the hot Jupiters. Let's look now at the various classes. So here we have the hot Jupiters, which around single sun-like stars exist around 1 in 200 stars roughly. So although they're the most numerous and the most prominent in this diagram, they're actually not the most numerous, the most frequent in the universe. They're rather oddballs in many ways. We have further out cold Jupiters, which exist around 1 star in 8, like the Sun, which means that the solar system is not very unusual in having one. And you can see they're slightly more massive than hot Jupiters, slightly more massive than Jupiter in general. We're not totally certain about those, whether they're less frequent or whether we just don't have the precision to detect those yet. And in between we have what we call the warm Jupiter Valley, of which we don't know too much yet about. And below, I think the more exciting population are the super-Earths and mini-Neptunes. You see planets that are more massive than the Earth, which is here, so more massive than there, but about Neptune and below. And we'll see why we call them through 2 different classes later on. And those are usually closer to this star than Mercury is from the Sun, which is really surprising. Something more massive than the Earth closer than Mercury is from their star. And about half of Sun-like stars have one. Half. This is crazy. And in many cases, they exist in multiplanetary systems. So you don't have just one, but you have several of them. And that's rather surprising. In many ways, this diagram is telling us that the solar system did not partake in the most dominant mechanism of planet formation. We're not part of a majority of systems. Less than 50% of systems look like the solar system, and we're not totally certain how many. So it doesn't mean the solar system is very special yet. However, what we see is likely not very representative of what happens, just by this very diagram showing that most other systems look different from our own. The difference between super-Earth and mini-Neptunes comes from this diagram. You have here the radius of the planet in units of the Earth, so the Earth would be at 1, Neptune would be about at 4, and the orbital period here for these various super-Earth and mini-Neptunes. And there's a sort of gap at around twice the size of the Earth. Closer in, it's a bit bigger than later on, but roughly about twice, 1.8 Earth radii, there is a difference. And it's telling us objects that have a large gaseous envelope, like hydrogen and helium, small versions of Uranus and Neptune, to objects that have likely lost that envelope of gas, which, although increases the radius quite a lot, is not very frequent. It's only 1 or 2% by mass. But they've lost it due maybe to irradiation, due to a formation process we don't really know yet. However, they have lost it and therefore remain a sort of bare core, maybe with an atmosphere that is a bit denser, like nitrogen atmosphere, for instance, like on Earth. So we're trying to find out this as well. Now let's look back here and compare to the solar system now. So Earth analogs, true Earth analogs, likely are around 1 in 10 stars like the Sun. And by the way, all of the numbers that you see here, the 1 in 200, 1 in 8, 1 in 2, and 1 in 10 here, are just for single Sun-like stars. All this diagram was for single Sun-like stars, which are rare. And in fact, there is a third axis that rises here, which would be stellar type in a sort of 3D diagram. And stellar type shows you how different and how similar stars are to the Sun. And this is within 10 parsecs of the Sun, so within a volume around the Sun. We counted how many stars there are and what the masses are. And Sun-like stars are here. You can see they're 1 plus or minus 1, 1 plus or minus 0.1 solar mass stars. And these only represent about 15% of the stellar content of the galaxy. And because single Sun-like star needs to be alone and half of the stars in the sky are binaries, as we've learned, then the diagram that you saw before was only concerning about 7 to 8% of all the stars in the universe. So maybe, the diversity is not just the various planets occupying a big diagram, but also the type of stars that are occupied at the center of the system. And in fact, the majority of stars are in this location here, less than a quarter of the mass of the Sun. And those seem to have more planets, in fact, more rocky planets than single Sun-like stars do. Therefore, there might be more Earth-like planets around stars unlike the Sun, like TRAPPIST-1 in a way, than around Sun-like stars. If there is one thing you should remember from this presentation is that half of the stars are binary stars, so they're different from the solar system. Half of the stars have masses less than a quarter than the Sun, so they're different from the solar system. And half are single Sun-like stars, so they look like ours, but they have a super-Earth in the system, and so they look different from the solar system. So a lot of diversity, very, very different systems. So does that mean that the solar system is very special? Well, maybe not. Let's look at the solar system and imagine what do we have in there, and try to remove one object and see how our perception of reality would be different and our observation of nature would be. For instance, if we removed Saturn from the solar system, what would we have removed in our sort of preconceived ideas before we detected exoplanets? Well, Saturn is the only object that is less dense than water in the solar system, for instance, so we would have removed that. We would have removed the grand rings, and maybe all imagination that such rings could exist. We would have also removed Titan, the biggest satellite in the solar system and the one that has an atmosphere, the only one that has an atmosphere, which may look like the primordial atmosphere of Earth. So you can see that removing one object, we would have lost a lot of knowledge. And in fact, if we look at the solar system, we find a lot of diversity. Titan and its atmosphere odd. The Earth-Moon system is very strange when you look at it, the rings of Saturn, of course. Venus rotates in a retrograde fashion, so while it orbits in one way, its planet orbits the opposite way. There's a big red spot on Jupiter, etc., etc. We have Chariklo, which is a small asteroid that has rings. We have Uranus that has a very tilted axis on itself. And there's a one-to-one resonance of Janus and Epimetheus, two satellites that have exactly, or more or less exactly, the same orbital period, but exchange ever so slightly the distance to their planet. So there's a lot of interesting things, and it may be that the nature produces in each system sort of 12, maybe 20 very specific, very unique traits out of a bag of 200. Let's say we have 200 type and the solar system pick 20, and another system will pick 20, out of which having a super Earth has a 1.5 chance, or having a low mass star like TRAPPIST-1 is 1.5 chance or something. So we're not totally certain yet. However, it shows how much imagination we can have just by looking at the solar system, looking back and seeing how much diversity there is there, and imagine, extrapolate that to exoplanets. So I hope you've enjoyed this presentation. Welcome to the university, and hopefully see you soon on campus.